for inviting me tonight for British Computer Society Advanced Programming Group and Internet Group. My name is Mehmet Oner Yalcin, and this is very briefly about myself. And I work for Sky on the service provider side, not the media entertainment part, but obviously the borders are blending as well. So I'm working day to day as a network data scientist. You might know, like, maybe data scientist is a person who just deals with the data a lot. Yeah, as it sounds. But we are specifically, our team is specifically working on the network data, the internet-related data. This is a kind of fusion of three different disciplines, like as a data scientist, so we do lots of measurements and then also try to make sense of the results. And we do also tool building, like today we are going to talk about, so it's more on the DevOps, development and operation side. And as well as it requires lots of domain knowledge. So my background is also network engineering, so I worked in different vendors and the service providers. So this is a fusion of three jobs, and my team members are also working on specific problems, but all related to the same areas. Normally I do build tools, or sometimes, like, whatever the measurements are done, I try to do some statistical analysis, or sometimes do some level of machine learning to understand, to group the different the results, for example. And daily I also do lots of coding on different platforms, like mostly open source libraries from R, if you're aware of statistical programming. Most of you probably from academia and the normal software world, they probably use R, and Python and SQL. So if you want to reach me out later, you can use my Twitter handle or LinkedIn or GitHub handles. Okay. So this talk is about not about network devices, because I previously presented this talk in the network automation meetup. So many of the people are from the network engineering background, and they are trying to automate the networks, which is like the trending topic at the moment. And it's not only about the programming either, so I try to keep the only programming part slightly light. And it's also not specifically about the data analysis, but it's just like building a tool for a specific purpose using different open source libraries and programs developed by other researchers involved. So, and it uses the basic tools, like most of you probably are familiar with, like ping or TCP scan. We are trying to discover the structure of the internet from a perspective of a commercial question. At the end of, we build a tool that does some automated measurements and also gives a kind of insights about the wider internet structure. So why do we call this tool as Hubble? So there is a kind of overlap what actually the Hubble does. First, obviously, the credits goes to Edwin Hubble, who is a great American astronomer who did lots of discoveries in the 20th century. And obviously, there is a very, very successful space telescope in his name. And it's still at the Hubble after probably almost more than 20 years. It's almost reaching the 30 years. This space telescope is still, we are getting lots of good measurements from the space, and we discovered space with thanks to Hubble Space Telescope. So what Hubble Space Telescope does is that it just focuses on a specific part of the space and gets detailed measurements using different tools. And then then we interpret them, and then we understand, like, the universe is expanding, or just like there's this galaxy and there's a neutron star there. So lots of the different discoveries are made possible by the Hubble Space Telescope, and it targets a specific part of the space and does this measurement. So pretty much, in our case, you want to target a specific part of the internet, and then do measurements, and then make sense of these measurements. So that's why for us, the internet is a kind of space where we operate, and then we need to get lots of different measurements and then collect those and then understand the results. So that's why we called our tool is Hubble. So what it does is it does also have, like, similar to space telescope, it has different things like probers sending like the active measurement packages and then receiving it back. It also does some discovery, host discovery, which is like, for example, you want to send obviously your probes, but you want to understand that the endpoint is going to respond you back. So this also does the host discovery, and it does also like the enrichment. So you get some measurements, but it's also what you do is that you enrich with other data sources your result, so that you can just, when you load into your database, you can look at from different perspectives. I will come to these points separately later. And it's basically a Python library, so it's a collection of tools merged together in a Python library, and then programmers or researchers can go and use this library to take measurements. And so, and in the back end, where all the measurements are collected, it also uses something called ELK stack, which stands for Elasticsearch, Logstash, and Kibana. This is a kind of set of tools, open source tools again. And so each provides like data manipulation and storage and also visualization. So that's used as the kind of data store and the visualization platform. So the story, how we come up with Hubble, is that it comes from a specific question that we were asked. Generally, our team is a kind of multidisciplinary team. We were asked some commercial questions first, like financial, could be like, for example, one of the questions were that we had 3 transit providers, which I explained. The transit providers maybe in a way that this is the exit points of a given ISP to the rest of the internet. For example, if you're talking to somebody on Skype in a different country, then that traffic between you and the other host and other end host needs to go through some paths. And for example, Sky has some installed network inside the UK, but it needs to connect to the rest of the internet, obviously. So these transit providers, also they are called tier 1 ISPs, they are connecting all these like national ISPs in the rest of the world. So they have different footprints. For example, one of them is called Level 3, it's an American company, and it has networks all over the world, so it connects to different ISPs. And their obviously economic model works like how much the traffic you use on level 3, then you pay that much. So what we want to understand is that each year we are renewing our contracts with these providers, and we want to not just do our decision based on the cost. So for example, for 1 gigabits of traffic at peak time, we pay X amount of pounds, for example. And they come up with saying that, okay, this is the amount you need to pay for the next contract. But we want to just look at not on the economic side. We want to understand how good performing they are. So this translates into our user experience as well. So if a person, let's say, playing a game which requires a lot of like low latency for them to enjoy the game if they're playing online. So we choose a good transit provider so that the traffic is delivered to another country rather quickly. So the question was like to measure the performance of a transit provider, and this needs to be done from the Sky's perspective, because if I will come to this point as well, why Sky's perspective is important. And why I mentioned here, it comes to the point where how the internet also works. The underlying protocol called BGP, Border Gateway Protocol, that's the kind of glue in the whole internet, connecting different service providers, and the whole internet based on this protocol called BGP. So Hubble was created to address this problem, and what Hubble basically does is that it finds the subnets of interest, let's say parts of the internet which is important to Sky, and then scans these hosts, saying that which ones are responding, would respond if I send a probe. And then after that, we discover this host, and then we do the measurement actually. So we send an active probe. Basically, it could be a ping or a TCP scan, and then we receive the response back. And then we also select different paths. So in our case, we had 3 transit providers, so 3 different ways to access to the rest of the internet. And we want to measure how these 3 would respond. So we are accessing the same endpoint. Let's say you pick up a point in France, for example, and you send the same probe. You send a probe to the same destination, but using a different path. And then the response you get, you just store it, and then after that you just do your analysis. And then we are also using it for different purposes, which I am going to explain as well further. More targeted measurements. There are different problems associated with measurements on the internet. One of them is that obviously measuring transit provider means that transit provider are the access to the rest of the internet. So your problem is becomes a kind of a bit more difficult problem because you need to measure the whole internet ideally. But obviously we don't want to do that one. It's just too much costly. So we want to understand if we can do some compromise, but if we just measure a small part of the internet, and then but still it will give us a good understanding of how our paths are performing. So there is one probability distribution law called, this is an empirical one called ZIP. It's hard to say, but ZIP law. And that one is telling that not all the things are, for example, let me give an example, it's going to be easier to explain through an example. For example, in English, there are lots of words, but not all the words frequencies are the same. So for example, and, or I, are, is, these are very frequent words. But if you choose some other word, like measure, and that's much less highly likely that you can across when you read the book. It's much less likely to come across. So the ZIP law is also valid for example, how many rich people there are in the world. Like there are a few number of very rich people, and there are many middle income and then also low income people. So this is the ZIP law, or you might also hear similar probability distributions like Pareto chart. It explains the distribution of these phenomena. And indeed, this is true for internet as well. So, for example, from our perspective, Skype's perspective, most of the traffic, let's say, coming from a very small number of addresses, let's say you're watching YouTube, you're watching Netflix, those are the biggest generators of traffic. So we definitely, this is a very subnet of interest for us. And but if you look at for something, I don't know, very about a specific type of dog breed, and there's a people who are talking about in a forum, that's probably is not very important place to look at. So we don't need to measure that area. So what we do is that we have some set of tools that can give us a result that this part of the the internet is generating lots of traffic for Sky. So this way we are identifying dynamically each day, to reduce the number of targets. And normally there are, at the moment, this is always changing and increasing, but there are 700,000 routes in the whole internet table, global table, and we reduce it down to around 500. This is quite a lot of reduction, so that only by measuring 500 routes, 500 subnets, we can almost get away with a good statistical power. So another problem with the nature of the routing, the internet routing, is done on destination. So for example, if I want to send a internet packet to one particular destination, I cannot choose easily which path I need to go. Because what I do is that I send one query, and then it ends up in one, let's say, next router, and the router looks at its routing table saying that, okay, I got this packet, and it has a destination IP address of something, and it's saying that, okay, then I need to forward from this link. So this is how the IP lookup works in a router, and basically this is something it's not something you can embed on the packet, saying that you need to go through these different paths, and you need to reach that destination through the different path. It can be done in different ways, but it's very, very hard in a global routing, mostly because you don't have access to the powers of the routing in a different ISP. So there are a few ways. The technical, I'll try to explain slightly this technical phenomenon, how we at least did it to some degree. Is that, so this is our peer and transit router, which means that this is the router where we are interfacing with the transit providers and the rest of the internet. And we have these probers sitting on three different subnets, different physical machines in DTM. And once they send this packet, for example, the subnet A is the transit provider 1 prober. What it happens in the peer and transit router, normally it should does the lookup based on the destination address, but we are configured specifically that peer and transit router to look up on the source address. So for example, if it's coming from transit provider prober 1, then it is going to forward it to transit provider 1. So that's a kind of technical hack we need to do, because otherwise you cannot really enforce to choose the outgoing path. And incoming paths, we want to also ensure the incoming paths from, let's say, because the measurements are like you send a probe and it comes back. So we want to also choose the incoming path needs to be from the same provider. So what we did is another trick. It's very much mainly used on the internet, global internet, is that we only advertise the subnet A to the transit provider 1. So this means that in the rest of the internet, all the people can access the subnet A, where our provider is sitting, only can come through the transit provider 1. They only know this is announced through only that route. So similarly, what we did also, transit provider 2 prober and the transit provider 3 prober, third prober. So this way, we ensure at least the measurement path is going to take the transit providers that we chose. So this requires a slightly custom setup, network setup, but this is quite essential for our experiment to work. And there were also some system requirements in general for our tool. One of them is that obviously you cannot do it most of the time. You cannot choose the destinations by hand, because it's a lot of amounts of lots of destinations. So it needs to be done dynamically and automatically. So that's done. That's one of the hard requirements. The other one is the scaling, because the number of probes we are sending is in the normal days about like 50 million probes. Maybe it's not a lot, but it can be even scaled further. So you can go up to a couple of hundred million, maybe billion probes you can easily go. But yeah, we are trying to restrict it to some certain degree, but it should be scalable, and it should be ideally horizontally scalable. Now, it doesn't mean that you need to have better machines, but you might need to deploy extra similar machines, so it can scale that way. And the microservice architecture means that it can, all the different features, for example, the prober can sit in one logical or physical entity, and the host scanner can be in a separate logical entity or a physical entity. So and they are not tightly coupled. They just talk to each other. Here is through a message bus. So it's just similarly kind of you do your work, and you don't need to be aware of. For example, let's say you're a scanner, and you receive a set of subnets, and then you do your thing. For example, you just identify the host in that subnet, and then you pass it into message bus. You don't need to talk to anything specific, and whoever later picks up, like the prober, is just they are going to see that they are receiving an active host that they need to probe against. So that kind of microservice architecture also gives us more scalability, and for example, tomorrow if somebody comes to do a development here, they can just focus on some specific part of the program. So they can program in a different language, for example. Let's say they want to have something more powerful and they go and implement it in C, but they have a good interface. They well-defined interface is just like that allows its microservices architecture. And the development effort should be like kind of, again, should be well-defined. All should be like a plugin architecture. So if I want a new feature, I define as a new plugin. So I don't need to know everything in detail. I can just implement this plugin and the well-defined interface. So that allows developers to join and then implement new features. The enrichment is another important part of this one, because we get a response, and based on the destination, for example, you want to identify in which ISP they reside. Normally, the ping, when you send a ping message, for example, you receive back and you receive, for example, round trip time for that probe, but you don't get much more metadata about that one. But so we enrich this ping result with some other metadata, like where the BGP information or geotagging. Then it gives us much more visibility about like where we are pinging and which ISPs or which countries. So that allows us to do more in-depth analysis. And the data analysis should be it should be scalable again, because we might have lots of data. And other thing is that we should be able to do a real-time do analysis, and shouldn't be lots of efforts from the person who is doing this data analysis. There should be a tool that it is easy to work with, and even non-programmers should be able to come and create their own views. And data visualization is also very tightly coupled with data analysis here. So you create a dashboard and you pick the data sources, and then you can, with a couple of clicks, without any programming, you should be able to create your views. So here might be slightly specific, like Arbor API and Cantic API for the who are working in the ISP environment might be familiar with these tools, Arbor and Cantic. They're mostly used as a security, like for example, if you have a DDoS attack in your network, these are the tools that tell you where it is coming from. We use those as a kind of also traffic analysis tool, like saying that these subnets are sending us lots of traffic. So for example, Netflix or Google or our own platforms like Sky video services. So similar, obviously Sky own services are in our network, but in different networks, like Netflix is coming from there. So that tells us which subnets are important. Or you can obviously put a static file. I'll come to this point as well. There was a specific case where we used static file. And then these subnets are identified and sent to host discovery. And for host discovery, we use this open source tool called ZMap. This ZMap, you can go here, and this is a nice project, also open source project, and they develop not just only ZMap, but a couple of other tools. And then they also run some scans internet-wide. And if you are doing some either academic work or some other internet-related work, you can download those ZMap files and then do your analysis. So what their scanner, the ZMap scanner, is also a very fast internet scanner. You can do internet-wide surveys with this tool. And if you have enough bandwidth, it even scans the whole internet, global internet, in 5 minutes. So it's very fast. So we use this scanner underneath to, when we identify the subnets of interest, we use ZMap to find the actual live hosts so that we can send probe into them. And this is a very kind of small code, just showing how does this one works. So for example, here the Sky prefix there's a sky prefix, and we want to scan this one. And then we just say we want to get maximum results of 50, and we also restricted bandwidth. Sometimes if you scan, let's say, remote host and you don't specify a bandwidth, then it might be understood as a also DDoS attack or some sort of attack. So that you can also, it's also nice internet citizenship practice that you just keep your bandwidth slightly low so that you don't cause any trouble for the responding hosts. So and then it responds back for a given subnet. It responds back with whatever the result. So it gives us maximum 50 results from this subnet. And then after that, identifying these hosts and hosts, we just go to the probers. This data goes through probers, and probers we use the Fiscaia's prober tool called Scamper, and this is in San Diego University Center for Applied Internet Data Analysis. There are lots of nice articles and tools as well developed for the internet measurement community here. And one of them is Scamper, and it's really capable of doing in parallel probing and in different, also responding but in a kind of structured data, which is, in our case, is JSON I was using, if you're familiar with the structured and the unstructured data. So it is very easy to use and do in parallel scanning, and as well as like receiving the structured data. So we as a program, we use the Kaida, and they just not only do network layer reachability probing like ping, but they also do UDP, TCP, and HTTP. I'm not sure HTTP, but I think HTTP and DNS should be also there. I need to check. So here is just like, if you remember in the host list, is like that host, the one in the previous slide, there was a number of hosts we discovered. So it goes to that host, and then we want to say that, okay, each 3 seconds, and you do the measurement, and then do it for 10 times. And I don't want to get on the statistics, I want to get the whole data, for example. This is a kind of how it's wrapped up in Hubble. And this responds back with the whole measurement, saying the round trip times. And maybe you can see on the top, there is something called ASN. This is the this is the number 5607 identifies, for example, Sky network in the whole global network. So if you receive like 179, for example, I think that was, for example, Cogent, for example, that's a global ISP again. And similarly, if you receive another number, then you know it identifies a Google host, for example. So that one is not in the this Scamper tool. This is like one of the enrichments I was telling you that it's appended here, which we're going to come in a moment. But obviously you can have the same data in a table format if you want to do analysis in R, for example, or Python, Pandas, if you're familiar with, or SQL. So this is the way you can get the data if you just change the only stats from false to true, and you specify the format as Pandas. When I was talking about the enrichers, so you get the data, you get the result. The Scamper, what it does, it adds the geo data. For example, this end host is residing in this country, like let's say France, Germany, or United Kingdom, and if possible, it's up to the city level, and as well as like it's adding this ASN identifier, the autonomous system number. So that is the part where we use the PyASN module, which is developed by TU Delft University in Netherlands, and it's a very fast lookup, the IP to ASN lookup tool. But I think we are going to not use anymore because the Logstash, which is already a part of our geotagging platform, when we're ingesting the data, they now support also this ASN lookup. So this is a great tool, but we are going to retire that one soon. And Logstash is also adding the network, the geographical information for the result. So once we have this measurement data, we store it in something called Elasticsearch. This is a NoSQL database. If you're familiar with NoSQL term, it's just just stores not the normal SQL data, but JSON blobs only. So this is a very fast also and open source platform for storing data and then doing computational analysis, text search, or like lots of different queries you can run on Elasticsearch, and it's very easy to scale. So you can, if you need more power, you can just spin up new instances and on different machines. And it also has failure. For example, if one machine goes down, the data is already replicated in other Elasticsearch clusters, so you don't lose anything. And Kibana is also is the same product, the same company's product. That's tightly coupled with Elasticsearch. Instead of you writing the code, Kibana is a visualization tool that you can just click and then access the data in Elasticsearch and query and create the visualizations dynamically. It's very straightforward for people who are not, for example, programmers, but they want to understand the data. This is very widely used as well. And the last thing is that how this communication is done between all these components. This is like maybe you might know that in some offices there is a message kind of platform, let's say. You put the message, or for example, in hospitals, for example, you take the sample, let's say urine sample, and you put it here, and then it just goes through some tube, and then you don't care where it goes, and the people who receives doesn't care where it comes from, but they process it, for example. Similarly, this is a message bus as well. So once you do your analysis or you do your work, you find your host, you just publish into the message bus, and whoever is listening is going to take those results from you. And this is how, as I said, microservices architecture works in our case, and that creates this kind of distributed systems architecture in our case. And for example, it's publisher. For example, publisher publishes once, and let's say publishes a lot of data, and the consumer one, for example, it cannot cope up with the amount of data. Then you can easily spin up another consumer 2, consumer 3, or whatever, and then they can just then empty the queue much faster, so that you can you have this kind of horizontally scalable system and parallelism. This is how our physical structure and how like these big blue kind of circly roundish things are our physical development environment and measurement environment. But also all these smaller like squares or round squares, they are the logical components, how they run. This, you can have different physical architecture as long as you satisfy your requirements, but in our case, this is how it worked, how it was working. This doesn't need to be, this is the ideal case. And how it's, I already probably told all the steps, but this is how it works from end to end. So subnet getter goes to RabbitMQ as a bus, and ZMap finds the host and puts it into our message bus, and the probers, different probers, pick up, and then they send the probes and get the results, and then put into the log stash where the geotagging happens, enrichment happens, and they put it into different Elasticsearch clusters. Our database, scalable database, and Kibana, you can access all this data from the visualization platform and then look at the results. So, for example, here is the one view of the from the Kibana. So here, for example, in this specific instance, we are looking at the 50 percentile, 95 percentile, or 99 percentile of the round trip time for different platforms. Like in this case, like 3 providers, namely NTT, Level 3, and GTT. And here, if you look at like GTT has a slightly better performance, but you can get this data in general, like as a for spreadsheet or something, but another programming platform you want to do further. So, and this is the time series graph in general, like from running from previous 6 p.m. from the previous day up to 5 p.m. today, 4 p.m. today. So if you see here, for example, GTT has a slightly higher standard deviation. Standard deviation is also known as jitter. So it's like if I send 10 probes, they all, for example, in general, on average, they come, let's say, 50 milliseconds. Return round trip time is 50 seconds, but not each probe always comes in 50 milliseconds. Sometimes they tend to come 40, 41 milliseconds, and another time is 60 milliseconds. So jitter, jitter is like this standard deviation between those probes, and this measures that one, and the median round trip time. So also, like if you remember, the geotagging is telling us that which countries, in this instance, for example, to the Lithuania, our standard deviation to Lithuania was higher. It could be, so that what we do is that we just go and dig through that one. Was there anything affecting to access to Lithuanian networks at that point? It could be on the transit provider side, or it could be like in one single transit provider. For example, if you see here, it's probably hard to see, but that's the loss as well. So loss to the different countries. For example, SG is the Singapore, I think it stands for. Loss for GTT is low, but loss for level 3 and NTT is high. So if you prefer like to reach this end host in Singapore, better you choose the GTT because it has much less loss probability. But in this case, for example, RS, I'm not sure which country is RS, but it's the second one is Hungary. So it's showing that which countries are like kind of showing more problems when you try to reach. So that's the point you pick up, and the difference between all these graphs is telling like which transit provider is having a better or worse performance. And so, for example, you can filter by country. Here is just on the top you can see that you can filter a specific country. In this case, it's China. You look at China. And in China, there's a huge difference now between transit providers. Like level 3 has a round trip time of like 300 milliseconds, which is quite high. Obviously, it's Asia, so it's a long way to get there. But GTT and NTT has around 200 milliseconds, which is a much better path. And around some time, you see, like if you look at the time series data, around between 8 and 9 a.m., which is possibly somewhere evening time in China, or just like around 12 and 13 hours. So that the jitter for level 3 is increasing. So probably there's a congestion happening on the level 3 network when you try to reach China. It could be on the somewhere along the path. So that's something you need to dig deep to understand where is actually this like bottleneck is happening in the level 3 network. So this gives us a lot of information. So if you want to exchange traffic with China, you better don't use level 3 in this instance. But obviously this can change dynamically, and this is why we run these experiments continuously. And filter by transit provider. So you can look at a single transit provider as well. This is also showing like you clear up the other transit providers, but you just want to look at from, in this case, it's GTT is a transit provider. And one interesting case was Limelight. Limelight is a content delivery platform, which means that if content delivery platforms are very popular platforms, like for example, delivering websites, or like in this case, it's mostly Limelight is delivering lots of media. So, for example, let's say I'm a company like Microsoft, and I want to roll out my new, let's say, Windows, not 10, but 12, for example. Instead of I'm delivering all these new Windows software from my servers, what I do is that I go to one CDN provider, in this case Limelight, let's say, and tell Limelight, okay, I give up this software to your servers, and you push into all servers all around the world, and people want, if they want to get this new Windows, let's say 12, they download it from your network. And we have, because the CDNs are global caches, So it's just like much easier to people to download it from. Limelight is important in this case. And what happens is that when we look at the measurement, here GTT and NTT has a higher round trip time, like around 90 milliseconds or 90 milliseconds. But level 3 is much better in this case. It's about 10 milliseconds. And from my hunch, because it's like 80 to 90 milliseconds, mostly that they tell like about, at least you're crossing Atlantic or somewhere. And 10 milliseconds to 20 milliseconds, they are saying that either you are in UK or Europe. So, and we are basically measuring the same destination. So this was a kind of interesting case for us. What happens is that then we do traced this route. And this is a GTT showing us like, what happens is that here's London, the sixth path is London, and the next one is like NYC, New York. So what happens is that the destination is in Europe, but first it goes to GTT, goes to London router, and then it goes to New York, and then comes back, and it offloads to another network, Limelight network, in Frankfurt. So it comes back and then connects to the Limelight network in Frankfurt, and then just ends the end process in Frankfurt. So this is a really long path. So okay, GTT is like doing something we don't really very much expect them to do, but it does, because it's the BGP, or the Internet Global Routing, is not just based on everything ideal routing, but BGP inherently puts all the kind of political or economical or social aspects of the networks. So for example, GTT prefers to peer up with Limelight only in Frankfurt, for example, for some contractual reasons. So that's why we can only reach Limelight from GTT through this weird round trip, like going to the US and coming back. And what happens in NTT is that if you look at again like the ninth step, it connects to GTT. So in order to access to Limelight from NTT, you need to go first NTT and then later GTT, and then it gives you access. So NTT doesn't even have direct peering with Limelight. So this is even kind of worse in this situation. And if you look at level 3 is just goes to London, and it also connects to another transit one provider called Cogent, but it connects in somewhere in Europe. So and the Cogent has access to Limelight. So it's the data, your path stays in Europe. So that's why if you're getting the data from Limelight, if you're watching something, prefer Limelight, sorry, level 3 in this case. And before I go to limitations, we did one another analysis. Because Sky is not only a UK company, we are operating in Ireland, Spain, Germany, Austria, and Italy. So we want to understand if we can deliver our media, like Sky Go or Now TV, whatever you're watching, to the consumers in Germany, for example, from UK. There's an economic side of this one. Instead of putting all the servers there, we can keep it in UK and use the transit providers to deliver that data. So and that was economically kind of viable for us. But we want to understand the users get a good experience. If they are getting like kind of, if their screens are loading all the time, that's definitely a no-go. So that's why, in that case, we just put the servers in Germany better. But in order to give this decision, what we do is that we just target 5 different German ISPs, and we, from the BGP table, we took their subnets. This is a static file where I was mentioning before. And then we discovering continuously hosting these 5 different ISPs, and then taking measurements from here to understand in the evening time if there's any kind of round trip time increasing or standard deviation is increasing on different ISPs. So better you don't pick that ISP or even transit provider paths for that ISP. So that was a good case for us to understand the path between us and the German ISP. so that we decide based on the outcome of these measurements how to move forward. Because it was a couple of, it's quite, in this exact level, decisions could be quite expensive, so you better have something to reason it. So that was another case where we used this tool, Hubble tool. And now we are targeting to our network, our different POPs. For example, we are targeting, let's say, we have like many different, operating in different cities. So we are targeting different cities and understanding like if there's any trouble happening at a specific time, that gives us a kind of alarm saying that, okay, the measurements are getting higher, the jitter is getting higher for this specific city. And then that triggers our operations teams to have a look at. But this is not fully implemented yet. This is the next project I will be possibly working on after I complete a couple of other projects in the pipeline. And the limitations, that is just like, this is just only we have two probers, TCP and the ICMP at this point, but you might add more probers like UDP probers or HTTP or DNS probers for different purposes. And it doesn't support IP version 6 as of yet. That's not an urgent requirement, but in the later we need to have IP version 6 as well. And how it interacts with some components like Scamper, it's not always ideal. I try to define here a bit kind of Python sub-process, all those stuff, but a bit of technical jargon here. So maybe a better integration would allow us to scale even much easily. So deeper level integration between Python and the underlying tools would be better. And then the parallelism, the asynchronous is also like there at the moment, but it should be even better, which is like could be the next steps for us to go. And yeah, the last thing is that installation is slightly tricky at the moment, but yeah, we need to put in a kind of something called container. People can download almost instantly, and then they don't need to worry about installation steps. That it's set up very easily, and obviously also these containers are the way to go forward for also parallelism and scalability. So that's another step we need to go and look at further. So while talking about Hubble, there's just as a side note, there are other projects running in the world. Like one of them is RIPE NCC. RIPE is a European kind of governing body for the internet. Let's say if you want to get new ASN number, if you want to set up an ISP, or if you want to get a new subnet, public subnet, then RIPE is the organization you need to talk to. And they also do lots of the measurements, and they also provide you probers, like some like Raspberry Pi kind of probers that you can connect to your home, and all the people around, like in the internet community, especially prober owners, they can use your prober to do measurements across the internet. So you earn some credit by plugging your prober, and then using that credit you can do lots of other measurements, which is also very useful. And there are also a few other measurement projects around the world, but I can also encourage you, if you're interested, to go to Central for Applied Internet department in San Diego, Vizcaya, and the ZMAP project is also a great place to look at the internet scans. I think that's it from my side. If you have any questions, very much.
Thank you very much.
Yes.
So do you currently use your Hubble just to serve Sky, or do you provide help to other companies?
Yeah, I'll just repeat the question. Do I use just only Hubble for Sky, or just for other the rest of the community? That's the real step. The next step we want to go is that we want to open source this one. Actually, we wanted to open source a few months back, so that people can contribute. People can come and use this tool and make the internet a better place, let's say, for measurement, and then they understand better. We haven't open source yet because the code, as I said, is not slightly tricky, and the integration is like less than a bit ideal. I didn't have bandwidth to work on Hubble project in the last few months. I was caught up in another project, but next project is going to be Hubble again. So at that point, I'll make it much nicer packaged, and then we're going to open source that one. And our department is open sourcing other products already. So it's a very kind of encouraged behavior in our department. So yes, we definitely want other people to use it, to see their results, I mean like their outcomes, what they share for the wider internet community, but also like kind of if they want to contribute and everybody can benefit from that one, we would very much like it. And I think that there's a kind of demand for this one in general.
Thanks. That's a very noble, thing to do. Thanks.
Yeah, the good thing is computer science or software engineering is that once you do something, your efforts is not like kind of cake. People, if you share, it diminishes. It's just like if you share, it just becoming more and more beneficial for everybody. It's growing, yes.
Yeah.
So that makes it even better. And people come and fix your bugs, or just they develop a new feature, and everybody can benefit from that one. And even it sounds noble, but it's also very practical as well for everybody. So it's a great place to work with. Also, it's very fulfilling for every probably computer scientist.
Thanks.
Thank you.
More questions? Yes.
Do you have issues around expiring data and how long you retain it for to get sort of long-term pictures or very short-term pictures?
Yeah. In our case, we were retaining data for about 3 weeks. It was because just only limited to our physical infrastructure at that point. And we were just interested in like only not very long term. But what we can do is that we can summarize this data. This Elasticsearch, the database, provides you an API. So, for example, if you want to like summarize the data and store it in a long-term database, like let's say another SQL database, for example, where business intelligence or analysts can use that data, you can do that one as well. But in our case, we haven't done that one. It's just purely depending on how much you want to retain and how much, let's say, storage area you have. You can retain up to 2 years, 3 years, or whatever you want. But it's just like produce a lot of data. Today, I mean, a lot of data is very kind of, if I talk about terabits of data generating many platforms, ours was generating about 15 gigs of measurements daily. And so it depends on how much you want to retain that kind of speed of information going into your storage.
Is the ping turnaround the only measure? I mean, do you measure throughput, for example?
Throughput is so the question is that do we only use ping or do we want to use throughput? Throughput is a great also way of measuring things, but in our case, it's like throughput is mostly there is one single problem with the throughput is that you need to get most of the time the consent of the end host for throughput. You don't want to really send a lot of data. So ping is a very easy way to measure things like round trip time or jitter. Throughput, in our case, there wasn't the huge problem because the ping and the jitter was showing us if there is a bottleneck in the network, because those things are increasing. Just ping is not going as a isolated case because it's contending with other network traffic in the whole internet. And if there is a increase in round trip time, then you understand there is already a problem somewhere along the path, and then you run the trace routing, for example, and then trace route tells you that path is taking slightly longer, and then that might give you more idea. So in our case, throughput was not entirely needed because we can infer this information from the ping. Yes.
More questions? I have questions.
Yes, sure.
You mentioned that you don't have currently support for IP version 6.
Yes.
What proportion of the traffic currently is version 6?
That's going to be a kind of rough guess from my
Yeah.
perspective. Yes, it's not going to be certain. For example, I can tell you just specific, because not everybody is implementing IP version 6, but like great internet giants like Google, Facebook, and Netflix, they're all promoting version 6 as well. And for example, today when you watch, let's say, movie on Netflix, in our case, it's mostly coming from version 6 platforms. And the other thing is that we also have dual stack. Dual stack means that you are assigned in your home, you are assigned a version 4 address and the version 6 address, but not all the ISPs has like version 6 at the moment. So if you need to talk to that ISP, you just need to only talk in version 4. Or if end host is only have version 6 and version 4 and there is no version 6, you cannot use version 6. But in general, the version 6 for the traffic generating hosts, like mostly media hosts like Google and Netflix, they are there, and that's picking up. I think my rough estimation, let's say, please take it. For Netflix and Google, it's most of the traffic in our network, but if you this one, it's probably 20-25% our whole network traffic. This is for Sky, but obviously it might change for different ISPs.
Also, in the past, I experimented by demonstrating students with tools like ping and trace route, how the internals of the internet are working and what strange routes sometimes the packet can go. And I noticed that recently it became much more difficult to find a host which will respond to ping, because it is wastage of resources in a way.
Yeah.
Which could be exploited as denial of service attack.
True. Yeah.
So is it difficulty in your case?
Depending on some like kind of networks, it could be the case. Sometimes if you ping an ISP and they let's say the end hosts are their users, home users, and their routers are like generic routers given by that ISP, and that router is like kind of not responding to that pings. Yeah, then from that ISP you might get slightly skewed results, because not all the you get much less data for that one. But in general, the tool that I use, the ZMAP, it is very successful finding hosts, and slightly you also do some kind of computation, like how much statistical power, or just statistically significant amount of hosts do I need to understand like reliably our measurement is. So we do a little bit of like kind of power analysis. Power analysis is a kind of term in statistical domain, let's say. So that tells us you need this much of amount of measurements to get this certain, let's say, confidence interval for your measurements. So we do before we sending the probing, we need to understand how much of data we need to collect as well. So most of the time, because of the size of the internet and the size of the subnets, we do get enough information to make it statistically significant. But definitely there could be some skewiness between different ISPs as well. If you have, especially this was the case, like for example, when we were measuring against Germany, not all the ISPs are responding at the same rate.
So is it any kind of agreement between internet service providers, to your knowledge, that they kind of encourage measurements, and because of that they tend to allow ping in the hosts, or it is not at all agreed by anybody?
It's not fully like, as far as I know, there's no like kind of agreement between ISPs specifically. And ISPs are generally like they're transporting the data. So end hosts are responding to bodies in this case. So ISPs not all the time controlling the end host. If you, for example, if you're running a server, let's say in a data center, and the ISP doesn't care about what you do with that server. So it's up to you to respond back. But obviously ISPs can block the ping messages inside their networks. But most of the time that they're allowing for the moment. Yeah. And there's another thing is that ping message can run on slightly technical, but ICMP packages, or you can use the UDP as well. It's most of the time, if they block ICMP, you can use UDP as a transport layer for your ping messages. and that might be also working. So there could be some get-arounds, depending on your case, yeah. But I think so far we can get a lot of measurements, because mostly our measurements are about, like, as I said, like 40 to 50 million measurements we get when we run against 500 subnets in the world.
Yes, you have a question? Yes? Ah, okay, one little question. If you can return to one of the slides where you show a dashboard.
Yes.
Yes. Is it any significance in the size of the letters here?
Yes, exactly. So this tells, like, the standard deviation for the Republic of Lithuania, in Lithuania, was the highest. So the jitter. So for example, I send a package, and one package returns back in, let's say, 10 milliseconds. Then the next one is coming back in 100 milliseconds. So it's not consistent. It's not like always sending, coming back in 10 milliseconds or, let's say, 100 milliseconds. So the difference between those packages are quite high. But at this point, it is like, there could be also problem with the number of hosts we are pinging in Lithuania. Let's say only there is one single subnet and there are 5 hosts in Lithuania. Then this could cause this standard deviation, or it could be really the case because there was a link connecting to Lithuania. One of the ISPs in Lithuania was congested. That could be another reason. So it depends on, like, kind of, you might need to dig deeper a bit further, so that other graphs can.
So that means that you very specifically probing Lithuanian hosts there?
We are not specifically targeting, but this is.
Or it just happened in the time when you pictured this?
What happens is that we choose the significant subnets, and one of the significant subnets was in Lithuania. So it's not like we choose exactly Lithuania, but for that day, one subnet, or maybe more than one subnets, were in Lithuania as an important subnet. And so we find hosts there, and then we ping them. So at that point, yeah, Lithuania was having the highest jitter at that point.
Yes.
Was any other republic sort of deviation far too far to put on that because it would actually go off the slide?
Yeah.
Yeah, say Latvia or Estonia or somewhere like that.
Yeah, could be. I mean, it's just in this case, like.
The closest here is just Sweden, very little.
Yeah, I mean, you can look at
And
Latvia,
Poland.
but the only thing is that maybe we don't have subnet from Latvia at this point. Maybe it's not, because that subnet is not generating traffic enough for Sky to be significant, maybe.
I see Bulgaria's on there and not Romania.
Romania is not there.
Yeah. So that's, Romania is also too big.
Yeah, Romania is big, but maybe what happens is that some companies, let's say, let's say Lithuania is hosting some media servers for some international companies. Because they choose Lithuania as the ideal platform, they got a good economic deal, let's say, with that data center. And that data center, we are downloading lots of contents. Our Sky users downloading lots of content from there. So maybe that's why Lithuania was chosen, but not Romania. We don't know the entire nature of the traffic at that point, but it might require a little bit of digging deeper, because we have access which endpoints we are querying for Lithuania, and we can look at the AS number, the autonomous system number, and it will tell, is it an ISP or is it, let's say, data center provider or content delivery provider. Then you might have a better understanding why Lithuania was chosen and why it is like high of jitter.
Okay then, I think we covered all the questions and the food and wine are waiting for us. Thank you very much to the speaker. And unfortunately we have not got a book today, which speaker gave us opportunity to bring it now. But the book will be sent, already sent from BCS to your given address.
Thank you very much, I very much appreciate it.
How do I reduce? How do I reduce the size so I can move? Um, Perhaps just go. Yeah. I would escape, or I'd do an Alt 4. Alt F4.